So in this video, I'm going to go through the reactions of alkanes. Alkanes are very unreactive, so there aren't many reactions to go through, but they can be combusted. And by combusted, I just mean burned in air. And when you're burning them, they will react with oxygen. So you've got complete and incomplete combustion. If it's complete combustion, you've got plenty of oxygen. Incomplete combustion, you've got limited oxygen. With complete, you're going to form carbon dioxide and water. If it's incomplete, you're going to form carbon monoxide and water. So again, the difference between complete and incomplete is the amount of oxygen. When you've got less oxygen, instead of forming that carbon dioxide, you're forming carbon monoxide instead, but you're always forming water. The dangers of incomplete combustion is that carbon monoxide is toxic. So it's not just enough to say dangerous or harmful. You have to say toxic or poisonous. They can also ask you to write equations for the combustion. They can tell you if it's complete. They'll tell you if it's complete or incomplete. So if we look at some examples, they could say, write the equation for the complete combustion of propane. So you would need to know the formula for propane. It's prop, so you've got 3 carbons in there, and the number of hydrogen is going to be H2N plus 2. So I double 3 and I add 2 and I get 8. So C3H8 is propane. I'm reacting it with oxygen because it's combustion and it's complete combustion. So I'm forming CO2 and H2O. Now all I need to do is balance 3 carbons, 8 hydrogens. I need 8 hydrogens. Now I've got 3 times 2 is 6 and 4 is 10 oxygens. So I need 10 oxygens on the left. It's easiest to balance carbon first, then hydrogen, and then the oxygen. If I do hexane instead, the complete combustion of hexane would be C6 and it'd be H14. React it with oxygen and I'm still forming CO2 and H2O. Balancing it, 6 carbons on the left, I need 6 on the right. 14 hydrogens on the left, I need 14 on the right. 6 2s are 12 and 7 is 19. I've got 19, so I need 19 over here, and that's going to be 9.5. So 9.5 times 2 is going to be 19. They could also ask you for the incomplete. So if I stick with hexane, C6H14, I'm still reacting with oxygen, but instead of forming carbon dioxide, if they ask you for incomplete, you're forming carbon monoxide and water. You can also just form carbon. So instead of writing CO, you could just write C and you would get the mark for that. But typically you do form some carbon monoxide. So balancing this, I've got 6 carbons, 14, 7 is 14. And now I've only got 6 and 7 is 13 oxygens this time. To have 13 on the other side, it's going to be 6.5 O2. So just be familiar with the products of complete versus incomplete. Once you know the products, it's just a simple matter of balancing the equations once you've written them. So that's the combustion of alkanes. There's also another type of reaction of alkanes called radical substitution reactions. And in these reactions, you react alkanes with halogens in the presence of UV light and you form haloalkanes. So an example, I've got butane here. I'm reacting it with chlorine, that's my halogen, in the presence of UV light, and I end up with a substitution reaction. I lose one of the hydrogens from my alkane and I replace it with a chlorine. So I still have my 4 carbons as I did before, but I've lost one of the hydrogens from that last carbon and I've replaced it with a chlorine. The hydrogen that is lost will pair up with the other chlorine from Cl2 to form HCl. So with these reactions, you need to be able to write a mechanism for the reactions in the form of 6 equations. And I'm going to do out these mechanisms. I'm going to do it 3 times because I want you to see that they're the same every single time. I've got 3 different reactions. In each case, I've got my alkanes. I've got propane, I've got cyclopentane, and this time I've actually got 2 chloropropane, so an alkane that already has a chlorine on it. So it's actually a haloalkane. And I'm reacting these with my halogen, and I'm going to get a radical substitution each time. So you're asked to write out a series of steps, and you need to know the names of these steps. And the first step is called initiation. And in your initiation step, you take the halogen that you've been given. So in this case, it's chlorine, which would be Cl2. I take the chlorine, Cl2. I react it with some UV light. And the UV light will cause the chlorine to break apart and form two chlorine radicals. So Cl dot plus Cl dot. If I do the initiation step for the next reaction, it's going to be the same. This time my halogen is bromine. So I've got my Br2. This time your halogens are always diatomic. I treat with UV light and I break it up into two bromine radicals. And for the last step, again, my halogen is chlorine. So my initiation step is going to be exactly the same as what I had over here. Cl2 in the presence of UV light, and I form two Cl radicals, which I could also represent as this. So I can write Cl dot plus Cl dot, or 2Cl dot. So that's going to be your first step in all of these mechanisms. Make sure you know the name, initiation, make sure you know the conditions, UV light, and make sure you can write that equation. The next step is called propagation. And in your propagation step, you take the radical that you formed in initiation and you react it with your alkane. Now, when you're using your alkane, or you're writing your alkane, you need to write it as the molecular formula. So don't try and draw the alkanes. You write it as the molecular formula. And the reason we always use the molecular formula is we don't know which hydrogen we're going to replace. And when you draw it skeletal, it can, just get a bit confusing. So we're just going to write the molecular formula of each of these alkanes. So here I've got propane. The molecular formula will be C3. It's prop, so I've got 3 carbons, H8. So I take my propane and I react it with my chlorine radical. And what happens is the chlorine radical pulls a hydrogen off the alkane. So when I'm doing my alkane, instead of writing C3H8, I'm going to write C3H7 because it's lost a hydrogen. That hydrogen has been removed and it's joined up with the chlorine to form HCl. Starting here with a radical on the left-hand side, I am going to have a radical on the right-hand side. That C3H7 is going to be a radical. I then take my C3H7 radical and I react it with a molecule of Cl2. When I do that, the C3H7 radical pulls the chlorine off Cl2, giving me C3H7Cl. And I form a Cl radical. So what you'll see here, your initiation step, you started off with something relatively unreactive, chlorine. You used UV light and you formed 2 very reactive chlorine radicals. It's called initiation because you're starting with something unreactive and you're making something very reactive. It initiates or kickstarts the reaction. In your propagation step, you take your reactive radical and you react it with the alkane. But in doing so, you generate another radical. You generate this alkyl radical, which can then go on and react with any Cl2 that you've still got knocking around. It can form the haloalkane, which is your product, and also forms another chlorine radical. So the reason this is called propagation is you start with something reactive, a radical, but the product of your reaction also contains a radical. Again, in the second step, I start with something reactive, a radical, but my product also contains a radical. So because you're producing another reactive species, the propagation step drives the reaction forward. You're always producing something reactive, you're always driving the reaction forward. It's a chain reaction. These 2 steps for propagation are going to be the same each time. So if I do the propagation over here, again, I'm going to write the molecular formula of cyclopentane. So it's pentane, so it's got 5 carbons. And usually, if it's an alkane, you do H2N plus 2. But because cyclopentane is a ring, I'll just draw it down here, because it's in a ring, each carbon only has space for 2 hydrogens, and you actually end up with C5H10. That's my molecular formula of pentane. So just as I did before, I take my alkane and I react it with the halogen radical. So in this case, I'm using bromine. And just like before, what's going to happen is you're going to lose a hydrogen. So here I went from C3H8 to C3H7. Here I'm going to go from C5H10 to C5H9. Here I formed a radical. I'm going to do the exact same here. And then the hydrogen that I removed from the alkane pairs up with the bromine and I form HBr. Then I take my radical just like I did over here and I use it in the next step. So C5H9. Here, my radical collided with some unreacted Cl2. Here it's going to collide with some Br2. And what's going to happen is you're going to remove a bromine C5H9Br and you're going to be left with a bromine radical. So again, you start with a radical, you end with a radical. You start with a radical, you end with a radical. Propagation, it's a chain reaction. It's going to keep going and going and going. Over here, we're going to do the propagation step. Okay, and this time it's 2 chloropropane. I'm just going to draw that for myself at the bottom. This is what I've got, 2 chloropropane. And again, I'm going to write this as the molecular formula. So if I count up, I can see I've got 3 carbons here, 1, 2, 3. I've got 1, 2, 3, 4, 5, 6, 7 hydrogens. And I've got a chlorine. I've got C3H7Cl. That is my molecular formula. So that's what I'm going to write, C3H7Cl. And I'm going to react this with my chlorine radical, just like I did before. And just like before, I'm going to lose a hydrogen. So I had C3H7, I'm now going to have C3H6. The chlorine remains, and it's going to be a radical, and I'm going to form HCl. I then take my radical, C3H6Cl dot, I react it with some unreacted Cl2, I end up with C3H6Cl2 plus Cl dot. Okay, so these steps are exactly the same each time. For propagation, you start with a radical, you end with a radical. You start with a radical, you end with a radical. It's a chain reaction because the radical you started with, that halogen radical, is regenerated in the second step. So it's going to keep on going. So that's initiation, propagation. Then your last set of steps is called termination. This is about finishing the reaction. And to finish the reaction, what we need to do is we need to get rid of all of these really reactive radicals, and we need to be producing products that do not contain any radicals. So what will happen is that in order to get rid of your radicals need to react with each other. In this reaction, I've got a chlorine radical, which could collide with another chlorine radical. And if it did, I get back to Cl2. So the radicals cancel each other out and I'm forming an unreactive product. The other radical I have, C3H7. So I have a C3H7 radical which could collide with a chlorine radical. And if it did, I would just get C3H7Cl. So I'm just adding the two of them together and I'm getting rid of the radicals. So again, I'm forming something unreactive. And my final possibility is my C3H7 radical can collide with another C3H7 radical. And I need to add these together. So I've got 3 carbons in each molecule. If I add them together, I'll have 6 carbons overall. I've got 7 hydrogens in each molecule. I add them together and I've got 14 overall. And you can see in my termination steps that I'm getting rid of the radicals. I'm forming something unreactive that terminates the reaction. In the next one, it's going to be exactly the same. It's called termination, and I take all of my radicals and I react them together. So here I've got a bromine radical. So I could have a bromine radical combining with another bromine radical to form Br2. I could have my alkyl radical, which in this case is C5H9 radical. I could have that colliding with a bromine, C5H9Br. And I can have my C5H9 and my C5H9 reacting together, adding these two together. So 5 and 5, I've got 10 carbons in total. 9 and 9, I've got 18 hydrogens. I'm just adding them together. And the last one is going to be exactly the same. Termination, add up all of your radicals. Again, I've got chlorine reacting with chlorine to form Cl2. I've got this C3H6Cl radical colliding with another Cl radical to give me C3H6Cl2. And then I've also got my C3H6Cl radical colliding with another C3H6Cl radical. Add my carbons together, 3 and 3 is 6. Add my hydrogens together, 6 and 6 is 12. Add my chlorines together, 1 and 1 is 2. So C6H12Cl2. All of those reactions are done exactly the same. They will give you the name of the alkane, they will tell you what halogen you are reacting it with, and they will expect you to write out this mechanism. They will expect you to include the names initiation, propagation, and termination. There's 1 initiation equation, 2 propagations, 3 terminations. Overall, this question is worth 6 marks. Same every single time, so definitely worth learning. The only other thing that they ask you on this is they can ask you for a limitation of the method. A limitation is that you can't control where the substitution takes place. So you could end up with, if I look here at my butane, when I drew this out in full, I put the chlorine here on the last carbon, but it could easily go here on the second carbon. So instead of forming 1 chlorobutane, I could form 2 chlorobutane instead. So that would be another potential product. I could also have more than 1 substitution on the same molecule. So instead of just forming 1 chlorobutane, I could form 1,1-dichlorobutane, or I could even form 1,1,2-trichlorobutane. So you can get multiple substitutions, and you can have substitutions at different points. This all means that you end up with multiple products, which will then have to be separated at the end. So it's not an ideal method for that reason. In your feedback sheet, section D goes through these reactions. You've got a few equations to write. Complete and then incomplete, so know the products. And then when I ask you for the mechanisms, you need to write out the 6 equations. When it says describe the reaction, you don't need to write words. It shouldn't be a written description. It should just be those 6 equations that I've just written out for you. Again, when you're doing these, don't use skeletal formula, use molecular formula. So work out the molecular formula of each of these. Even if you have to draw it first, that's fine, but work out the molecular formula and write out the 6 equations exactly as I have done. Press pause, have a go at them for yourself, and then press play when you're ready to see the answers. Okay, so we'll start with the combustion reactions. Hopefully these were okay. Butane is C4H10, and it was complete combustions. You're forming CO2 and you are forming H2O. Octane, C8H18, again complete, so it's CO2 and H2O. And then nonane, that's 9 carbons, it's going to be C9H20, and again with complete you're forming CO2 and H2O. So it's just a matter of balancing. You can use decimals, you could write a fraction, so 6.5, or you could put it as 13/2. You can do a top heavy fraction. In the last example, you're asked for incomplete combustion, so instead of writing CO2, I'm writing CO, hexane, C6H14, and then you balance your equation. So hopefully those were okay. Then I asked you to describe the mechanism for the following radical substitution reactions. No descriptions needed, no written explanations. You're just doing initiation, propagation, and termination every single time. So you got your initiation step, using the UV light, include your conditions. Then you take your alkane, butane is C4H10. Remember, use molecular formula, don't draw it. You react with the chlorine radical, you form this alkyl radical. That then reacts in the next step. You form your product with a chlorine radical. So you've got you're regenerating your chlorine radical, which is why this is propagation. It keeps going and going. And then you've got your 3 termination steps. Remember, at the end, when you've got these 2 alkyl radicals, you're literally just adding them together. So you've got 8 carbons and 18 hydrogens. If you were asked for an overall equation, it would be the alkane that you start with, the Cl2, your haloalkane product, and the HCl. That would be your overall equation. And they can ask you to write that from the propagation step. I just want to show you in your propagation step that you end up with a Cl radical on the left and a Cl radical on the right, so they essentially cancel out, and you end up with this radical on the left and this on the right, so they cancel out, and what you're left with is C4H10 and Cl2 as your reactants, so I've written them here, and you're left with C4H9Cl and HCl, which I've written there. So that's your overall equation. The next one, cyclohexane, is going to be the same. So I've drawn myself cyclohexane, so I can see that it's C6H12, so not the typical general formula of an alkane. Other than that, everything is the same. You just remove a hydrogen, C6H11, and you're adding the bromine instead. When you're adding these two together, 6 and 6 is 12, 11 and 11 is 22. If you were asked for the overall equation, again, you've got a bromine radical on each side, which cancels. This radical will cancel, and you're left with C6H12, and Br2 goes to C6H11Br and HBr. The last one, 2-methyl propane. So again, I said draw it first so you can check your molecular formula. You can see I've got 1, 2, 3, 4 carbons, and I've got 3, 6, 9, 10 hydrogens. So the molecular formula is exactly the same as butane, which means your answer for number 3 is exactly the same as your answer for number 1. Your overall equation is the same as well. Okay, so that's absolutely fine that they're exactly the same. If you're using the molecular formula, that is what you end up with. As I said, these questions come up all the time. They're worth 6 marks. They're the same every time, so it's well worth the effort to learn them off.